Well, thanks everybody for inviting me today to give a talk. I'm really excited to chat with you all. I'm a planetary geologist by training, and I just started as an assistant professor here at ASU in the fall. So yeah, I'm really excited to get to know campus better and everybody who participates in our programs. So thanks for the invitation. A quick little bit of background about me. Like I mentioned, I just started as an assistant professor in CC 2 months ago, 3 months ago, who knows, fairly recently. And before that, I was a research scientist for 6 years at the Laboratory for Atmospheric and Space Physics at the University of Colorado Boulder. They don't tend to do a lot of planetary geology there, but they do tend to do a lot of planetary atmospheres, especially Mars atmospheres. So I was on a floor with a lot of the MAVEN folks. MAVEN is an upper atmosphere Mars orbiter that I will proceed to not talk about again in this talk because I work on Mars Reconnaissance Orbiter, a different orbiter from MAVEN. But there's a lot of strong Mars research there. And then before that, I was a postdoctoral research scientist at Planetary Science Institute in Albuquerque. What I was doing there was actually finishing up the last several months of the Dawn mission at Ceres. So in addition to it being a Martian, occasionally or frequently, I like to think about how icy asteroids work in our solar system, both in terms of retaining water, but also where did they come from? How does it relate to the origin of Earth's water? And then before then, I know Shield Your Eyes. I got my PhD in 2018 from the University of Arizona's Lunar and Planetary Laboratory, and my bachelor's degrees are from Northern Arizona University. So I've been jokingly telling people that Arizona Board of Regents, I would like a commemorative plaque for I have completed the trifecta of working or getting degrees from every public university in Arizona. But I imagine they are otherwise occupied right now, so I'll just put that in my back pocket. And so here are some logos of some different projects I've worked on. Some of them are currently active, some of them I'm still currently working on, some of them have finished. But really, Mars, Moon, and icy asteroids are most of my research. But today we're going to talk about Mars because I think it makes for a really interesting kind of contained topic. And is also where, because of the HiRISE camera, we're still getting new data today. And so it's really exciting then to be able to look at the historic data. We're in this period where 20 years ago, Mars Reconnaissance Orbiter was on its way to Mars. It had launched in August of 2005 and was going to arrive in March of 2006. So we're in that period where 20 years ago, MRO was somewhere between here and Mars. Um, and so I figured I'd talk about that mostly today. And so this might be a review for a lot of you, but I figured I kind of start off with the basics. One of the reasons we are really interested in studying Mars, and I know I said I'm a geologist and I am not going to talk a whole lot more about the upper atmosphere, but one that's really critical, especially for Mars polar regions, is just like the polar regions on the Earth, which is how is the overall climate of a planet particularly working? And so in the case of Mars, we have a really interesting example where most of its atmosphere is made of carbon dioxide, in contrast to our atmosphere, where it's mostly nitrogen and then a little bit of oxygen, carbon dioxide, and other gases as well. So what's unique about carbon dioxide is it emits and absorbs light in the infrared. So we're really not talking about the kind of light that our eyes can see, but the kind of electromagnetic radiation that causes temperature. And so this is a very cartoon picture of this. But light comes in from the sun, reaches the surface after passing through the atmosphere. This heats up the planet, you get to some sort of equilibrium temperature, and then energy from the surface is re-emitted to space. And if you didn't have an atmosphere or didn't have clouds, this would pretty much be the energy balance of an entire planet. So if you're trying to do the energy balance at the surface of Ceres, you have light coming in, thermal radiation leaving, and your modeling is so much easier. You don't have to worry about those pesky clouds or anything happening in the atmosphere because you don't have one. This is also applicable to the present day moon because there's not enough material orbiting the moon to really count as an atmosphere, or there's not enough material around the moon to really count as an atmosphere. And then this is where atmospheres start to get tricky and to start affecting the radiation balance at the surface, which is where I'm interested in this whole diagram, is that you can also you can also transfer energy in the form of temperature from the Earth's surface to the atmosphere. And then what happens is depending upon um, also the characteristic of your atmosphere can also absorb energy itself. So the thing to kind of think about here is that when you're sitting in your car outside, it's always a little bit warmer than you'd expect, and it's because some of that heat has actually been trapped. Sometimes it's called a passive greenhouse effect, but literally for the Earth, it's a greenhouse effect. And so then you have radiation from the atmosphere back to space, but then you have radiation back to the surface as well. So instead of there being a really nice single source, single sink, or single way of removing energy from the system, it gets a lot more complicated because now you have two components. And this interaction between radiation from the Earth's surface to the atmosphere and radiation from the atmosphere back to the surface is how you can have things. If you've heard about the runaway greenhouse effect, it's where this process becomes the most important in energy transfer in a particular planet's atmosphere. The current hypothesis is this is what happened on Venus, is there was enough carbon dioxide and other energy absorbing gases in the atmosphere that basically this feedback got so powerful that if you ever do the calculation for what the surface equilibrium temperature of Venus should be just based on its distance from the sun, it's very different than what the actual surface temperature of Venus is, as inferred and then sometimes measured by Soviet spacecraft that the Venus atmosphere then melts, hours later. And especially for the Earth, one thing that really matters is also the carbon cycle. So we're talking about CO2 playing a really important role as a gas that in our atmosphere that absorbs in the infrared. And so this is a schematic from the NASA Earth Observatory that kind of just shows you all the different sources and sinks of carbon dioxide on the Earth. And so these are plants, these are oceans, these are people burning fossil fuels. And so it is a fairly complex system, and with that, there are still really good atmospheric models that can tell you what's going to happen based on the amount of CO2 in the atmosphere. But part of the challenge of dealing with climate change on the Earth is that there are so many different things going on. Picking which thing is going to affect climate the most in a positive way is challenging, beyond the fossil fuels. So things like carbon dioxide recapture and carbon recapture is really important. But then where do you put that carbon? Do you put it back into plant biomass? Do you put it into the subsurface? And as a Mars scientist, I really love Mars because basically none of these things matter for Mars. There are no people currently on the surface. There's no plants currently on the surface. If there are aerobic bacteria anywhere on Mars, we sure haven't found them yet. There's also no liquid water ocean. There is a line of interpretation of some Mars surface data that suggests at one point there could have been large amounts of liquid water on the surface. Large amounts for some period of time of liquid water all are, depends upon who you ask right now. It's still an active area of research. And at least for the time being and for the last, 3-ish billion years, oceans on Mars don't matter for Mars's energy balance, especially if you're looking at it today, because today Mars has essentially no permanent liquid surface water, and so that's not really a place where you're going to have carbon capture or other things going on. So if I just put a giant X through a ton of these things, what's left in that kind of Earth climate schematic that I showed you for Mars? And so for Mars, we're going to focus on the carbon dioxide now rather than the oxygen, or not the oxygen, rather than the overall atmosphere. There's two ways of removing carbon dioxide from Mars's atmosphere. One of them is forming rocks called carbonates. I know you all are from all over, but if you're in the American Southwest and have ever tried to dig a hole in your backyard to plant a tree, and you hit this giant, like massive white deposit that's really hard to get through, that's caliche, that's carbonate deposit here. So carbonate deposits exist on at least the Earth and Mars, in terms of terrestrial, so rocky planets. And on Mars, what's really unique about putting things into rocks is that the weathering rate on Mars is so low that carbon dioxide almost never comes back out. And so once you go there, it removes it. Another thing that's really interesting about Mars, and one of my favorite Mars facts, is most of Mars's atmosphere is made out of CO2. And a significant fraction of that CO2, it gets so cold on Mars that it actually freezes onto the surface. So this image here is of the permanent residual ice cap on Mars at the South Pole. It's a little misleading because this is not the seasonal ice. This is something that is there year round, but the brightest stuff here is actually carbon dioxide ice. So it gets cold enough on Mars to form dry ice out of the atmosphere. To kind of think about an Earth analogy, that would be if it got so cold on the Earth that nitrogen would freeze out of our atmosphere. That just doesn't happen here because that's not how nitrogen gas really works. But on Mars, the major component of its atmosphere actually becomes solid for some periods of the year. And when you look at spacecraft data from Mars, especially landers that have a pressure detector, you can actually see Mars's atmospheric pressure change seasonally as the CO2 ice comes and goes. So it is in some ways a much similar or like much simpler climate system than the Earth. And on the other hand, it is like in the traditional definition of the world, totally alien from what we have here, because we don't experience, at least on the Earth, these big pressure changes because you're physically removing our atmosphere and then putting it back in. So that's really cool. Um, and then the flip side of this is that in whatever hemisphere you're in, when it starts to warm up again, the CO2 sublimates back in the spring. The temperatures and pressures on Mars are such that you're not going to get liquid CO2. So what basically happens is your CO2 condenses out as a frost in the fall and resublimates into the atmosphere in the spring and never really goes through a liquid phase. And I alluded to this earlier because Mars's weathering rate is so low. Basically, once CO2 gets stuck in a rock on Mars, it's probably never going to come back out. There are a couple of reasons for this, and one of the biggest things that happens on the Earth that doesn't happen on Mars is plate tectonics. So here on the Earth, you will have your continental and your oceanic plates subducting, or sometimes you'll have in the middle of a plate a volcanic eruption to add new land. All of those things will affect the lifetime of carbonate rocks. That process doesn't happen on Mars. So Mars, the entire surface is solid in the present day. There are examples of volcanoes on the surface, but they have not been too geologically recently active. And there's not a whole lot of evidence about whether or not there was ever plate tectonics on Mars. Kind of like whether or not there was ever an ocean on Mars. This is one of those side topics that you can really get into in research, and a lot of researchers have. The current balance of evidence is it looks like it's very likely that Mars really never had significant plate tectonics. So we can say that once you put CO2 in a rock, it's not coming back out. But this seasonal process and seasonal frosts happen every year, which is great and cool. And it's something we can see in the present day. And this is, in some ways, one of the major climate drivers on Mars is the temperatures get cold enough, CO2 freezes out. This is going to be the thing that's going to affect your weather on Mars pretty significantly, especially in the polar regions. However, what we're observing today on Mars, we really don't think has been Mars's kind of climate conditions for an extended period of time. And this has to get down to the obliquity of the particular planet. So if a planet has essentially 0 degree obliquity, what happens is the poles don't tilt, or the hemispheres don't tilt towards and away from the Earth, or not the Earth, the sun, in any sort of seasonal way. It rotates exactly perpendicular to its orbital plane, and there are no seasons. Everything's kind of about the same. What's interesting in this case is that if you have enough topography at the poles, you can actually create shadows in places like inside impact craters that never see the sun. So you can actually get some really cool ultra cold regions, which is what's happening on our moon and potentially Mercury and other places in the solar system. But it's something that's not happening on Earth or the Mars. And so obliquity is this measure of how much the spin axis is offset from being perpendicular to the orbital plane of the solar system. So in this schematic here, this is what a 45-degree approximate obliquity would look like. I think that's half of 90 degrees, and these slides are old enough that I'm going to trust that I did this correctly the first time I made this. But that's about 45. That's about 20. So the smaller the obliquity, the closer to perpendicular it is. And currently on Earth, our obliquity is about 23 degrees. It does vary, but it doesn't vary widely because of the moon. And on Mars, the current obliquity is about 25 degrees. And so just like a spinning top, these things vary over time. And so when I said Earth's obliquity doesn't vary much because of the moon, what we're seeing here is a plot in time for thousands of years. 0 is today of Earth's obliquity. We've got a 22.5 and a 25.0, which are enough to make a big difference in terms of ice ages and things like that on Earth, separate from the amount of CO2 in the atmosphere. But it's not as big as Mars. So for reference, this is a one of the classic models of Earth obliquity variation, or not Mars obliquity variation over time, and with Earth's obliquity variation superimposed on top of that. So Earth is about 20 to 25 degrees. Mars doesn't do that. So I think the minimum here is about 10. The maximum is pushing about 50. This plot is in terms of millions of years. 5 to 10 millions of years in the past, it's not too bad to predict Mars's obliquity. But beyond that, it actually gets into chaotic solutions where it's really hard to tell what solution is correct because all of them could be valid. This is because Mars has two little potatoes of a moon for moons instead of a relatively large compared to its size moon. So Phobos and Deimos, Mars's moons, are not doing a whole lot to damp these obliquity changes. And this is the other big driver and big determiner of climate on Mars is its actual obliquity. So this is, again, a really simple climate system where most of the temperature or most of the climate is set by the amount of CO2 you have and what your current obliquity is. For reference, this is what a 3 times change in solar radiation on the surface of the Earth looks like on the panels on the left. So a 3 times difference in solar radiation is the difference between the amount of sunlight you get at the Earth's poles versus the tropics. And as someone who spent their first August as a resident of Tempe this summer, oh boy, does 118 feel bad compared to like 20 Fahrenheit, or at least different. So those, though, are relatively small compared to Mars's insolation or kind of surface radiation changes. If you look at this bottom panel now on the plot, the top panel, so obliquity over time, except now time is going negative in the right direction, in the right-hand side direction. But insolation is this measure of solar radiation. And so in some of these obliquity extremes, you're getting 500 watts per meter squared. And then some of the other extremes, you're getting 100. So this is a 5 times solar insolation difference. So the difference between a high obliquity and a low obliquity excursion on Mars, the entire planet goes through a transition that is like going from the amount of energy you get at the Earth's poles to the Earth's tropics. So again, not only is this planet very weird because part of its atmosphere freezes out onto its surface every year, on these millions of years or tens of millions of years timescales, you're going through what on Earth we would consider just absolute nights and days in terms of the total amount of radiation you receive at the surface, and so what the climate might be like. So to take kind of a pause here to recap, the Earth has biology removing CO2 from the system in the ocean and in force, and it has primarily at this point humans re-releasing it. The plate tectonics carbonate recycling process does have some effect. But yeah, I drove to campus in a gas car today because it was the weekend and I didn't want to figure out the buses. It is people causing climate change on Earth through the release of CO2. It would be good if we stopped that because well, that was a 3 times solar insolation change is a massive change in Earth's climate. So far, and this is my Earth science pitch, not being an Earth scientist, so far, this is the only planet that's even remotely close to some planet that humans and other life can live on. So I would like to have a livable planet, and this one so far is it. Flip side with Mars, though, and the reason why we want to do Mars climate science is that it's a much simpler system. There's many fewer parameters, and so being able to understand how other terrestrial planet climates work help us refine our understanding of how the Earth's climate works. And so on Mars, there's no global scale biology operating in the present day, and carbon dioxide is primarily cycled through the polar deposits. So now on to one of my favorite things to study on Mars, maybe my favorite thing to study on Mars, are where the ices are today. So on Mars, there's a lot of buried water ice, which is fine and good and excellent. You can see it through exposures from small impact craters. So because Mars has a thinner atmosphere than the Earth's, a lot more rocks from space make it to the surface to cause an impact on the surface of Mars. And some of those impacts kick up water ice. So we have a pretty good idea from that where currently buried water ice is. I don't talk about it in this talk, but Mars Odyssey, which arrived, I think in 2001 at Mars, was really interesting because it carried a neutron spectrometer. Neutron transport is very sensitive to hydrogen, and so using that, they made a global neutron count map of Mars. Places where neutron counts are lower are likely where hydrogen is higher, so OH, H2O, all those good things. And those maps of where water was inferred to be buried from the neutron spectrometer data matches so well with like these impact craters. It matches well with the radar studies that have been done, because if you also radar the surface, you can actually see where their material contrasts in the subsurface. A lot of those are consistent with buried water ice. So it's very cool and very neat. I'm deeply basic and I like my water ice just right on the surface. So what's nice about Mars is, in addition to all the buried water ice, it has two polar ice deposits, which are shown here in elevation data and in cross section, including with radar here at the very bottom. This is actually a radargram of the North Pole. And so based on modeling and observations and gravity data and all sorts of different types of remote sensing, we know that the seasonal ice on Mars is pretty much CO2. The North Pole of Mars and most of the South Pole ice, shown at elevation here, is water ice with some amount of dust in it. The South Polar ice is a little bit dustier than the North Polar ice. We know this from radar and from gravity measurements. And honestly, for optical measurements as well, the South Polar ice looks darker than the North Polar ice, and you do that by adding small amounts of lithic material, so a little bit of dust. And so we've known since the 1970s that these are water ice deposits on the surface of Mars. And I think I'm going to now proceed to tell you all the things we don't know about them that make them fun to explore. So we've known about these for a while. We know what their composition is, but there's this really beautiful layering. And this is, I think, the first HiRISE camera image in this talk. This is the North Polar layer deposits. And so these are alternating layers of up to about like 5% on average dust and water ice. The different colors and the different brightnesses or darknesses are caused by different amounts of dust. And kind of like an ice core on the Earth, we think these layers records how these different climates affected the amount of ice deposition here. And so if we can take this image and pair it with this obliquity over time plot, all of a sudden we finally have basically ice cores on Mars. And if you are interested in terrestrial climate science, ice cores are just absolutely critical for understanding terrestrial climate. This is great. The answer is probably yes. This is an idea that has been around since the 1970s, and I think a lot of us have not found any reason to refute this. New signal analysis and signal processing technique papers really suggest that there is some sort of climate signal in this layering. But one challenge on the Earth with terrestrial ice cores is that you can put a volcanic eruption with a specific date. You know it deposited ash inside this ice core, and then you can go, okay, so like this ice core, then this is the kind of like horizon of this particular year. We can't do that on Mars, in part because there haven't been recent volcanic eruptions, and also because we've only been constantly observing the planet for I think we're almost in Mars year 39. Every Mars year is about 2 terrestrial years, and Mars year 1, I think, is in the mid 1950s when we started making consistent telescopic observations of it. So in terms of trying to understand climate or even weather, this is a really short duration. So we have issues in being able to use these layers as ice cores in terms of absolute timing. We don't have it in space. You can't do the same sort of radiometric age dating that you can on the Earth, mostly because, and this is going to sound kind of facetious, but this is kind of our big problem right now, is that the kind of laboratory instruments you need to do that really solid radiometric age dating are literally too heavy and too delicate to be launched into space on a rocket, spend 18 months in space getting to Mars and then landing again. And they're also very power hungry. And I'm sure you know, the further away you get from the sun, the amount of energy you lose is pretty significant. And so sunlight on Mars then is a very precious resource. And so having a really heavy, a really power hungry, and a really delicate instrument to do radiometric ages is not really good. ages I'm going to show here, or anyone's going to show you, are going to be based on a calibrated lunar impact crater chronology. Also, it's not clear from different lines of evidence if the two ice sheets on the surface of Mars at either pole are gaining or losing mass in the current climate. And most geologists will tell you that the present is the key to the past, or the past is the key to the present, one of those two ways. And the challenge is that we really do not quite understand the present yet. So a lot of my work since my PhD dissertation until today has been trying to understand the current polar ice conditions. The dots here indicate every impact crater on the surface of the North Pole layer deposits. And I think for the interest of time, you're going to have to trust me when I tell you this is not a lot of impact craters, considering how much Mars gets just battered by impacts, which indicates a really young surface age. It's a surface age that's so young, this might be one of the youngest confirmable surfaces on Mars. And so being able to relate, and this is an image of one of these icy craters. You're going to see more of these. A lot of these impact craters have this bright material, and I think just a couple of weeks ago we confirmed with one of our spectroscopy colleagues that this is water ice. It's not carbon dioxide ice. So that's really interesting because water ice is what makes up most of these stacks of layers. And it's one of those things where we can see the carbon dioxide ice come and go every season, but we really haven't been able to see something equivalent for the water ice. So it's really cool, literally and figuratively, that this icy crater is water ice. And so we want to be able to link that back to previous climates and things that might have happened in the past. So if we can say, hey, the North Polar layer deposits are accumulating water ice at this rate, and we can characterize the current atmosphere through a lot of remote sensing observation, then this is what reasonable previous atmospheres or previous climates could have been that would have deposited these layers. So this is something that one of my undergrads turned postbacks. She's applying again for grad school this year, so we're hoping that she will finish writing this paper before she leaves us. Is looking at changes in these ice lenses and these small craters. And so these are data from Mars year 29. So this is almost 10 Mars years ago. So if you multiply that by a little bit less than 2, this gives you an idea of the terrestrial year this was first taken in, all the way up to Mars year 35. Like I mentioned, we're currently in Mars year 38. So we saw some more years of data, but what was remarkable about these Mars years is they were in between global dust storms. So it was a relatively kind of like quiescent period in Mars's climate and weather. And so what we're seeing are small changes in these water ice lenses. They're not big, they're not dramatic. Some of these might still be CO2 frost. This is something we're trying to understand right now, but we can actually watch things change on the surface of Mars, which might seem trivial today, but we're looking at HiRISE images that have, so these scale bars here are 50-meter scale bars. So we are seeing changes that are on the size of less than football fields on another planet. So that's pretty cool. That's why I go into work some days, is just see how Mars is doing today. Another project we've been working on is, so at the edges of these ice stacks, there are these things that look like powder avalanches. An arrow here is showing one of them. These have been observed since the beginning of the HiRISE mission and when HiRISE was starting to take data. They're on these extremely steep scarps. So this is a digital terrain model that we were able to make from 2 different HiRISE images. So zero slope here is in blue, high slope here is in red. It's almost vertical. So that exposure of layers I was showing you, if you actually look at how the topography data, that's an almost vertical slope, which again, almost vertical slopes are really hard to make in nature. And it looks like bits of them are falling off. But what's really interesting about these avalanches is you don't see any rocks here that have been obviously moved. So whatever is happening is not doing a whole lot of like geomorphic work. So you're not getting new or different features because of these, but they are happening a lot. And the reason I say they're happening a lot is that MRO orbits, every, 10-ish, 8-ish hours around the planet. We see these scarps maybe once every 2 weeks for the duration of South Polar Spring. And we see avalanches in a shocking number of these images. And then there's one beautiful image along this scarp in particular, where there's 3 or 4 avalanches happening at the same time. So we are looking at these scarps so little that to see avalanches at all means they must be happening almost constantly. And so it appears to be really constrained by seasons. So the L sub S here is um, the subsolar point or the solar longitude. What's important to think about is that this is how we measure seasons on Mars. So instead of going, hey, it's March in the northern hemisphere, we're like, hey, it's L sub S, just 95 or like 100 to like kind of indicate we're kind of more in the summer, like later spring. And so LSS 0 is Mars New Year. The next one will be in 2026. Hopefully, someone will have a Mars New Year party because it won't conflict with a terrestrial New Year party, and that's a big old good nerd thing to do. All the way to the winter in the northern hemisphere down here, and so 360s back here. All these avalanches appear to happen within basically 45 degrees of L sub S, between L sub S about 5 and L sub S about 50. This is when the sun is finally coming out. Polar night is indicated on this plot because we are so far north that this is where the sun doesn't rise for significant periods of the Mars year. And so what we think happens is that the sun goes down and this cliff gets ultra cold, and then as soon as the sun rises, that thermal stress is enough to start cracking pieces of this scarf off, which does happen on the Earth in some places, especially at Half Dome in Yosemite Valley. Thermal fatigue is definitely something that happens on a lot of terrestrial planets, but between Mars's thin atmosphere and the fact that we have this contrast between polar night and then the sun finally rising after, weeks and weeks and weeks and not seeing it, we think this is a really unique situation where the thermal stress is causing this. However, no one's been able to quite determine that it's actually thermal stress for sure, so that's some ongoing work, and stay tuned on that. And then we've been talking about the North Pole of Mars. There is the South Polar ice on Mars as well. One thing that's really nasty about this is, like I said, cratering is a way we tell relative ages. All of these craters, except for this one on the left that is nice and pristine looking, look like they've seen better days. And honestly, I think they're, especially Crater and Panel B here. It's kind of how I feel at this point in 2025, kind of mowed over by other things happening around me just a little. And so these craters take a long time to modify. So there are more craters on the South Polar layer deposits than on the North. So that means they must be older because more impacts have had time to form. They're also more modified, which means that this surface has been intermediately active in the past. And so what we're trying to finish up with this project is doing a really nice South Polar crater catalog and to understand what areas of the South Polar ice are more heavily cratered than others and what that means for surface age, but also whether or not this ice sheet in the South Pole is acting like one giant ice sheet or it's a bunch of different ice sheets kind of pancaked together. We think it's the latter, but again, this is work in progress and something that hopefully, as soon as I can start writing some more here, get written up soon, at least from the crater statistics standpoint. And then to really zoom out, this is a project that one of my PhD students is working on. It's a collaboration between us, CU Boulder, where my PhD student is, and the Smithsonian Institution. And we're trying to complete, or we will, it's almost done, it's very exciting, a United States Geological Survey science investigation map of the South Pole. So what we're looking at is 70 to the pole. So it's going to include the South Polar ice, which we see in different maps as either blue or blue and green here, but also the surrounding terrain, because in geology, your surroundings matter a lot to understand the context of what's happening. What's special about USGS science investigation maps is they have really rigorous standards. And so we are making a data product, but at the same time, this data product is really helping us interpret, like I mentioned earlier, are there multiple ice sheets kind of pancaked together? Is it one ice sheet? Because ice sheet deposition is so clear, like on the Earth, on Mars, pick your favorite planet with an ice sheet that was deposited there. How those ice sheets and when those ice sheets are deposited is absolutely critical for understanding where the water is on Mars in its atmosphere at any given time. And so we were probably seeing some stack up of Mars polar ice sheets. And like I mentioned, this map is so close to being done. I think we're going to submit it to the USGS in the spring. And so what's also really nice, except for right now when USGS websites are a little bit shaky, is that when these publications come out, these are publications that you can download and print out yourself. And they are open access data. So you can look at them and put them into your favorite GIS software and start thinking about what this means for both the geologic context, but different images. And so I've mentioned this a lot, and I figured I'd give some time to HiRISE here a little bit quickly at the end. So HiRISE is the high resolution imaging science experiment aboard the Mars Reconnaissance Orbiter. Like I mentioned, MRO was launched in 2005, over 20 years ago now in August. So, just over 20 years ago. It's managed by the University of Arizona and was built by Ball Aerospace before it became BAE or was bought out by BAE. And so there, I put an arrow here to indicate where HiRISE is on this illustration of MRO. We're being pointed at the surface because that's where the cool geology is. Though other instruments do look to the side, especially Mars Climate Sounder, because they're interested in looking at the atmosphere. And as you know, atmospheres extend a little bit above where the surface is. And so this isn't 20 Mars years, obviously, because a Mars year is longer than an Earth year, but this is a really significant monitoring data set. And the reason why, especially with polar science, Mars Reconnaissance Orbiter is my favorite orbiter by far. You can tell the other orbiter teams I said this, is that Mars Reconnaissance Orbiter, actually every orbit goes almost exactly over the pole. So this is a schematic that was published in 2008. So we're missing a lot of the other Mars orbiters like Trace Gas Orbiter and MAVEN that we have today. And the Phoenix lander is on here. The Phoenix lander was managed out of Tucson, and apparently that was always a little bit of it was not their favorite name. But the Phoenix lander was a rebuild of Mars Polar Lander, so it was literally a spacecraft rising from the ashes of a previous spacecraft. So Phoenix was an appropriate name. But you can see here the orbital tracks of these of Mars Express, Mars Odyssey, and Mars Reconnaissance Orbiter. And Mars Reconnaissance Orbiter, getting back to the idea of obliquity and tilt over your orbit, has an orbit that goes almost exactly over the pole. And when your orbit is on the order of tens of hours, you get a lot of polar coverage with Mars Reconnaissance Orbiter. And so it really makes it a place where you can take these monitoring series really easily, and you can take a lot of monitoring series over a long period of time. So all this to say is that there's a ton of polar coverage. And I wish I had enough time in my day to go through all the absolutely beautiful images we've taken, especially in these polar monitoring series. I don't. And if any of you would like to look at them, please send me an email, because there are a couple of things that we do need to analyze that have just been not on anyone's front burner for a long time. And it would be nice to move it there. And then in another shameless plug for HiRISE, HiRISE is one of the few instruments, perhaps the only Mars instrument, where members of the public can suggest observations. So if you go into HiWish, if there is an image of Mars's surface, either a place of Mars's surface that's never been imaged before, or something that you think would be interesting to look at, again, you register using an account on the public's suggestion page. And then what you can go into then is this software GUI. This is one of the first things I learned how to do in grad school, and so it's been not updated since. And so it's like coming home, being able to see this, because this is how I collected data for my dissertation, and this is how I'm still collecting data today using HiRISE. But what it asks for is a title. It asks for a science rationale. This is what the science planners will actually look at. Sometimes science rationale can be because it looks cool, and then that has a different level of potentially impact than saying, hey, we're going to look at this crater that we've looked at a couple of other times to see if we can observe active accumulation on Mars. So like the science rationale doesn't have to be long, but it has to be something that appeals to the science planner, so they'll try to schedule it. And usually special notes are not that important. And then what we have here is a little map. And so what I did is I just threw in literally the North Pole of Mars. So this is exactly at 90 north, 0 longitude. And so you can tell all of these different colored dots mean something in terms of an image that has been suggested or acquired with HiRISE. I think the purple is a different footprint from a different instrument. I should know this, but I don't look at the purple ones, so I'm not 100% sure. But this will kind of show you what coverage is already in the area, and you can go, hey, maybe imaging exactly at the pole isn't what I want to do. Maybe I want to look at something down here just to see, if the surface of the North Polar layer deposits looks all the same kind of around the pole. It doesn't. The North Polar area deposit has surface texture that changes. It's probably due to direct condensation of water vapor, but I don't think anyone has really mapped out every texture in every location. The other thing with HiRISE, when it's 25 centimeters per pixel at our highest resolution, um, taking a unique image of everywhere on Mars is going to take forever. Right now, our non-unique coverage as a percentage of Mars's surface that we've looked at, I think is about 5 or 6%. And again, it's been in orbit for almost 20 years. So this is definitely a really great tool for looking at really small things, but maybe less of a good tool for regional analysis. So you can kind of see how both the science questions I'm asking and using HiRISE data for are kind of informed by each other. So that's part of being a practicing scientist, is that as much as we think science is alone in a room coming up with a brilliant idea, sometimes it's going, hey, what does that look like over there? Oh, that's weird. Huh, we should take another image in a different lighting configuration to see if it's the same. And so a lot of times really interesting science comes out of, well, we have these instruments. How can we remix this data to address one of these broader questions about Mars? Science generally. So that brings me then to kind of a quick summary. And again, not to be too reductive about this, but Earth's climate system is complicated by life, and Mars is not, at least in the present day that we're aware of. And the more we can link Mars's climate history to things happening on the surface, in the geologic record, the better understanding we have of how another terrestrial planet operates in terms of atmospheres. I think I emphasized climate change a lot in this talk because it is one of the big things that we're going to need to confront as a society on the Earth. The other thing is that as you start to see more Earth-like exoplanets that have majority CO2 atmospheres, I think it's really important to remember that a planet that we've been studying, probably second best to our own, we have many clues, but we don't have an overall story, and Mars's climate history is by no means a solved problem. So when someone says, hey, it's a rocky planet with a CO2 atmosphere, it could be habitable, uh, sure, it could be. Or it could be a Mars, which in and of itself is really cool to look at and really interesting and tells us a lot, but it also tells us about the variety of terrestrial planet exospheres. So the next time you see, or atmospheres, so the next time you hear discussions of an exoplanet atmosphere, this is a really great up close study example of potentially one of those atmospheres. And hopefully we can get many more, and hopefully more of the exoplanet atmosphere folks will start talking to the Mars climate folks, and we can have some really interesting and interdisciplinary discussions there. And I think that is my last slide, and I am happy to take any questions. I think if we still have time left here, Tyler.
Oh, wonderful. Yeah, great job. Thank you so much. And yeah, I'll leave it open for questions. Everyone, you can unmute and ask away.
I have a question.
Oh yeah, for sure.
So you had the images of the craters. I think it maybe was like 4 or 5 slides ago.
Mhm.
I think that I might have missed the significance of those. And because you were saying that some of them looked like they had been modified, and I'm assuming that that was by, oh yeah, that one.
Yeah.
Yeah, and I mean, as far as I've been taught so far, is that Mars is completely inactive. Is that what you guys are looking at, the possibility of geological activity?
We are looking at the possibility of geologic activity, and Mars is incredibly active in these very specific ways. So if it has to do with the volatile processing, the CO2, seasonal CO2 comes and goes every year. And the thing to emphasize about this is that there has been a very large discussion about whether or not the North Pole or the South Pole or any of these surface ice deposits are currently accumulating in the present day. There have been contradictory lines of evidence from other remote sensing techniques. But we can see this ice lens change with our eyes. So at least this very specific place on Mars is gaining a little bit of mass. And it's a little bit of water. So this is that connection between the climate we can observe today and the geology we can observe today that we absolutely have to make before we can make good extrapolations about what past climates would have been like on Mars from the geology. Does that make sense?
Yeah, yeah. And so that's why you're bringing up the possibility of like the avalanches being caused by heat rather than the geological activity.
Right. So
Okay.
this might be exactly leaving a dark piece of paper out on your porch in Tempe in the summer where the thermal stresses are causing this. But these are all examples of, and I think this is one of the big, if I can get on my soapbox a little bit, one of the big revelations coming out of Mars Reconnaissance Orbiter is that Mars is not active in the sense that the San Andreas Fault is active, where like you have these big dramatic geologic changes over short periods of time still happening somewhat frequently. But there are these places on Mars where the surface is still changing. Like there's still an atmosphere, there's still things happening on Mars. So this idea that Mars is like in any way a dead planet is really thinking about global major volcanic eruptions potentially, but its surface is still being modified and things are still changing because of these volatile processes. I didn't even talk about the fact that we can see dust devils with HiRISE. It's very cool to see a dust devil on another planet from above. So we know dust devils are happening. We know we can actually measure sand dunes moving
Wow.
with HiRISE. And so there's a lot of things that are kind of wind-driven aeolian processes and a lot of processes that are driven by volatiles that we still know are like totally active. Like I mentioned with the avalanches, we don't see these things because they're happening rarely. Otherwise, we'd see much fewer or none of them. Um, Basically, with a spy camera around another planet, like you have to get lucky to have seen like the one example of this. So we actually expect these things to be much more frequent than even what we're seeing. And like I mentioned, we're seeing lots of these avalanches. We've gotten a couple of really spectacular dust devil images. And so, yeah, Mars is really still an active planet. It may not be active globally. We might not have big, charismatic volcanic eruptions like a Mount St. Helens happening every 100 years. But we're still seeing a lot of change and a lot of activity that directly relates to how its climate behaves. Because sand dunes moving is based on wind direction and wind strength. These things are potentially based on how heat moves through this particular type of material. And the small craters are examples where we can see kind of direct addition of water ice on the surface. So, um, yeah. So the next time someone says Mars is dead, you can go, actually, and really get some bonus points that way. Um, but yeah, and I think that's one of the big results from Mars Reconnaissance Orbiter is that after Viking and that kind of era of exploration, we weren't seeing these big changes. But then you put together the right set of instruments, and then all of a sudden, these changes pop out at you.
Right. Um, wow. Thank you.
Oh, for sure.
I have a question.
Yeah, for sure.
In regards to those avalanches, would any kind of seismic reading be helpful in determining more detail as far as when it happens or like how much or whatnot?
It'd be interesting. I think one of the things is that seismic data is always difficult because, especially on Mars, there's enough wind that, like from the InSight mission, the InSight data processing people for the seismometer had to be really careful that the wind wasn't pushing the spacecraft and then causing a seismometer reading because your seismometer is so sensitive. The other thing is that in these locations, it gets completely covered in about, 6 feet of CO2 ice. So if you did have a seismic station, it would have to survive being buried in CO2 ice. I know I mentioned the Phoenix lander very briefly. What did the Phoenix lander in was nothing on our side of the engineering. It's because it got buried by this 6 feet of CO2 ice and its solar panel snapped off. So that's gonna be part of the challenge of monitoring these in place is that these are really extreme environments. It also have to survive polar night, which is much longer than lunar night. And that's one thing that, especially in the lunar exploration program, is a really big challenge right now, is how do you keep your spacecraft, especially if it's on the surface, warm enough when the sun's not shining on it. So I think seismic data would be interesting. It would be interesting to see if there is obvious trigger seismically before we saw the avalanches. Also, one thing that InSight was able to pick up that was not actually any sort of internal Mars quake was InSight was able to detect new small impacts forming nearby. Um, and so that is also really interesting because it means that then you have this ability to kind of like see what the transmission frequency is, and you can do all these really cool geophysics applications. And so I think the answer to your question is yes, it would be interesting. I think there's a lot of engineering and data processing challenges to getting something useful out of that. I think what would be really neat would be a something that can measure either the heat flux or some sort of measurement of the actual stress at the surface. Um, Another challenge we have, and this is kind of a soapbox about this current project, we have is that HiRISE is 25 centimeters per pixel. Mars Climate Sounder, which I mentioned briefly, is one of the ones that kind of looks off to the side and looks at the atmosphere. We have Mars Climate Sounder data when we're flying over these scarps on MRO because they're on the same platform and they're taking data at the same time. The problem with Mars problem, we love all the data we have from Mars, but the problem with Mars Climate Sounder is its footprint is about 6 kilometers. So going from 25 centimeters per pixel to, and usually the center color strip in HiRISE images is usually about a kilometer across. So going from about a kilometer across to about 6 kilometers across is really difficult to then go, oh, this is the same location at the same time, which again is a very nerdy how do we calibrate data to each other problem, but it gets to this idea of how do you measure the temperatures and the atmospheric conditions at the same time these avalanches are happening. Which again, sometimes I'm like, oh yeah, my data don't match perfectly, and I should have done it this way. And maybe like for MRO2, we can do it this way. And then the flip side is we're sitting here basically being able to look at in both the infrared and invisible images what appears to be like an avalanche on another planet. Like this is pretty, I mean, it's not perfect, but like how cool is it that you can take multiple wavelength observations of essentially a weather or a geology phenomena happening on another planet. So I think this is a very long way of saying seismic would be great. More data is always great. I think there's a lot of challenges with it. And I also hate to say this as a Mars exploration scientist. Um, we're getting to a point where new data is always cool, but I think we have enough data in a lot of ways that people haven't looked at that there's still a lot to learn from this incredible data set. Just because enough people haven't looked at it, or the right person with the right science question or the right perspective, maybe from terrestrial remote sensing, hasn't looked at it to find something else. So new data are always cool, but sometimes the old data or data that you're currently collecting and the historical collection of like similar data really reveal some interesting things. Like to go back to these craters, to go back to these craters, yeah, if you just had, Mars year 30 data, you would go, oh, that looks fine. That's fun. Um, as opposed to like Mars year 34 data, where all of a sudden there's all this more bright stuff here. And then this is still what gets me and what I annoy my post-bac student who's working with me all the time is that this was actually between Mars year 34 and the Northern Hemisphere and Mars year 35 was a global dust storm. And all of a sudden it looks dustier. But this should have been covered by 6 feet of CO2 when the global dust storm was happening. So why does it look dustier? And there's so many things we don't understand yet from just taking our standard data that it is very cool to then think, okay, what's next? I think this is also where a pitch for keeping currently active missions funded is another big one. The reason why we're able to actually see these things and to have this really like beautiful data set. So LCBS is here in the corner. So again, measure of season. There are a couple of years where we didn't quite hit it exactly on the same day of the year. But within 10 degrees of LCBS, we were able to take multiple images of the same crater. This thing's only 50 meters across on the surface of Mars. So keep our current missions active. And yeah, if anyone here in the group is interested in engineering a engineering a lander that will survive being buried in 6 feet of CO2 ice for 6 months, that would be cool. You should do that. I think a lot of Mars scientists would be really interested in figuring out how to do that so we can get things like seismic or direct temperature data on the surface. The other thing about Mars Climate Sounder is that there is some amount of modeling that goes into determining what the surface temperature is. If you could take in situ surface temperatures at the North Pole, that would just be very wild and very cool, especially over the course of an entire Mars year.
Thank you.
Some great questions. So then I did have someone in chat ask about helping you with some images. So I did share your email. Hopefully that
Perfect.
was okay.
Yeah, I don't should have
Uh,
put my email in here. Yeah, please shoot me an email. Being a professor now, this is literally my job to work with students. And if you want to look through, you know, 2 terrestrial decades of Mars data, shoot me an email and we'll see what we can slice off and start getting this analyzed. Um, Again, it's one of those things where not only is it super cool to look at, the other thing is that having people use the data is the reason why we do this. I was the scientist responsible for a planning cycle, I think 2 weeks ago. The cycle's still in process, so I still am on the hook for making sure like science things happen, but a lot of the science decisions got made 2 weeks ago about what images to take. And there's nothing that makes us from that planning perspective feel better than going, oh, that person used this image to do something really cool. We're really glad we took that data and took all that time and effort to put it together. Because yeah, we really like exploring, but the problem is that, you know, if we have 8 hours a day to look at this, at some point we got to sleep, at some point we have to, you know, eat lunch. And so the more the merrier always in these kind of big data sets.
okay, cool. I appreciate you offering.
Yeah, well,
Okay.
and the nice thing is all these databases are online as well, so it really lends itself to I mean, a lot of these projects, when I started, I had to measure it in a GIS software, which it was nice to have a computer that could handle it. But if you're compiling images and saying, hey, did something change and where did it change? You don't need a whole lot of specialist software. You mostly just need a computer with a big enough monitor to look at it. So it's this kind of image analysis that's really transferable and really straightforward to do remotely. So I think it's a very, very good undergraduate intro project. And then you learn how the instrument works, and then you get the exploration bug, and then you never leave, and we get to keep you around for, you know, MRO2 whenever that happens.
That I just read it, his response. No, it sounds good. I love it too. I think that all sounds awesome.
Great. Well, yeah, shoot me an email and we'll see what we can do. I mean, I didn't talk about this a lot, but I got my start as an undergraduate looking at Themis and CTX data. And Themis is now, you know, across Tempe campus in the Moore building. So when I'm saying, hey, you can stick around for the next orbiter, that's literally people in the Mars community have done this. So that is literally possible. And yeah, like I said earlier, the more the merrier. We like sharing things in science, and we like when yeah, students can get their start going. Oh, and I didn't read my own slide. This black scale bar is actually 100 meters instead of 50 meters. So everything is about twice as big as I previously told you. But that's why we write down what's on our scale bars, as opposed to just having a scale bar and then trying to remember what the scale bar was.
Totally fair. Well, beautiful. I mean, I sure loved it. Are there any other questions to get out there before we?
Yeah, I had a
Oh,
final
yeah.
question.
Mhm.
This was a great talk. I was just wondering, so you mentioned the change of the axial tilt, right?
Mhm.
And I was wondering if that change of the axial tilt is solely gravitational nature, or if there are any like secondary causes to it, because I feel like there should be.
So it's mostly gravitational. And the trivia question that if any of you go on to do a graduate degree and I'm on your committee, this is fair warning. This is a question I ask everybody, which is what causes this jump at 5 million years? So most of this is gravitational. This jump is caused by the gravitational pull of Jupiter on Mars because Mars gets close enough to Jupiter.
Mhm.
So most of it is kind of that resultant like angular momentum variability that hasn't been dampened by a moon because it's going around the Earth. But every now and then Jupiter appears, and you can see it in the reconstructions. So you do have to take Jupiter into account when you're doing Mars obliquity and orbital reconstructions because it's out there pulling on it pretty significantly and causing, pretty significant jumps, right? Because the minimum went from, 15-degree obliquity to 25-degree obliquity. That's a big obliquity change. So yeah, it's gravitational for the most part. There are some more random variations that are harder to account for in the past, but yeah, this is all just the sun, lack of moons, and Jupiter kind of making an appearance. The challenge in this kind of research is, I think, in some ways, less understanding exactly how the gravity works, but starting to get back to these time periods when you have non-unique solutions because, it's hard to then go, okay, so this is what Jupiter was doing 50, 100 million years ago, and exactly how that trickles down to effects on Mars. So I think it's safe to say this is mostly gravitational. We're all talking about kind of conservation of momentum and conservation of angular momentum. But the details get a little bit fuzzier the further back you go. And so what people start to do is they start to add a kind of a Monte Carlo um, simulation part of it, or other simulations to try to understand that. So a lot of the Mars obliquity research that's going on now is orbital dynamics research about how you evaluate probabilities of things that happened in the past. And then one footnote to that is that 5 million years is not that long in the geologic record. We have surfaces, especially at the south pole of Mars, that are rocky that we think are much older than this, probably closer to about 3 billion years. And as a geologist, I always like to say, well, no matter what cool orbital solutions you come up with, if you precipitate your entire atmosphere out onto the surface and that's a prediction of your model and we don't see it in the geology is what happened. So that's another kind of cool interplay of like the geology is what happened, and this obliquity reconstruction is what could have happened. What are the probabilities of this happening? Because after a certain point, there's a lot of chaotic, non-clear steps to model much further into the past. Does that make sense?
Yeah, but do you
Wait,
think like some interaction in the core has to do with the change of the axial tilt, or do you think that has nothing to do with it?
good point and a good catch. So one of the big previous adjustments to Mars's orbital situation was when the Tharsis volcanic range appeared. So this is a thing where there was a large concentration then of mass in that volcanic province. And so it actually does change the mass distribution in the mantle, which does actually affect how Mars spins, which will affect like the total angular momentum conservation. And what's really neat is that we think Tharsis happened late compared to all of Mars forming. And so that's another like the geology is the proof in the pudding of the simulation is like no matter what simulation you have to have Tharsis appear and readjust whatever your orbital tilt of Mars is at about the right time. And you can figure out those timings from looking at impact craters superimposed on these volcanic provinces. So again, I think it's one of these things where we think, orbital dynamicists and geologists never talk, and then we have problems like this where you clearly need multiple different types of expertise to put everything together. So we should be talking if we're not already.
Yeah, thank you.
Thank you. No, this was wonderful. I don't know. I really appreciated it. I know that for sure. I think the questions also show everyone really appreciated it.
Yeah, thanks for having me.
Um,
It was really exciting to be able to chat with you all and spend my Saturday thinking about Mars, even though I did spend my Monday through Friday thinking about Mars. That's hopefully something that you start to notice about science is that it is something where it's a job where you're encouraged to like the thing you're doing. And that's one of the reasons like I'm so happy to have this career is like this we get to figure out how another terrestrial planet works. You get to go poke this system and then you get some spacecraft data and then you go, now I have 10 more questions. This stuff is a lot of fun. And so it was great to be able to spend a Saturday afternoon sharing it with you all.